Okay, welcome to our Friday Compass seminars. Today we have a presenter from across the pond, right, at UK. It's a pleasure to introduce Dr. Michael Haigh. Quick background for Michael. He completed his undergraduate degree in mathematics at the University of Leeds, followed by his PhD at the Maths Department at Imperial College London. He worked with Dr. Pavel Perlov, who you may know from his seminars at Rasmus. And Michael was working on eddy mean flow interactions. And then he continued a little bit working with Pavel as a postdoctoral associate at the Imperial College London, focusing more on eddy-induced tracer transport, the topic of his seminar today. And he will start a new role very soon at the British Antarctic Survey, right? Looking at something different, looking at melting ice sheets and sea level rise. So hopefully we'll hear more from Michael in the next few years on a new topic. And today he will talk about the eddy-induced transport and ways of representing this transport in ocean model. So Michael, please, the stage is yours. Go ahead.
Thank you very much. Hopefully you can all see my screen. So yeah, I'm going to talk about a full tensor approach to parameterizing eddy-induced transport. So this work is done with a group of us at Imperial College London, so myself, Pavel Perlov, and also with a couple of researchers, you guys over there at the University of Miami, so Igor Kamenkovic and Yulang Liu. So I'll start with a few slides worth of introduction. So this is a talk about the role of oceanic mesoscale eddies. So I'll start by giving a broad definition of those. We define those broadly as turbulent motions in the ocean with scales on the order of 10 to 100 kilometers. So just to illustrate, this image here is a snapshot of the observed sea surface height anomaly in the global ocean. The darker reds and the darker blues here indicate the stronger mesoscale eddies. So the eddy activity is strongest in regions like the western sides of the North Atlantic Ocean, the North Pacific, and in the Southern Ocean. But I would also like to get across that mesoscale eddies, despite being stronger in regions like these here, are present in the entire global ocean. So it's well understood that they play a key role in forcing the large-scale circulation. And it's also understood that they play a key role in forcing the large-scale distributions of passive tracers. And it's this second part, the large-scale distributions of passive tracers, that we're going to be interested in today. The main problem that we have when it comes to mesoscale eddies is that they typically cannot be resolved in numerical ocean models. So the solution currently to this issue is that we have to parameterize these effects that are missing from our coarse resolution ocean models. So I'm just going to illustrate this problem from a mathematical standpoint as well. So let's say we have some eddy-resolving tracer equation. This represents the evolution of the tracer on some isopycnal surface. So I'm going to talk today about isopycnal tracer transport along surfaces of constant density. So our tracer C here is advected by some full complete eddy-resolving velocity U and subject to some other forces. What we're really interested in this equation is the role that the eddies, the mesoscale eddies, play in forcing the large scales. So one way that we can examine this large-scale tracer evolution is by writing down the corresponding equation for the large scales. We can do that by defining our large scales using some kind of filter, which I'll denote using an over bar. Then this equation 2 here, we can just write down the equation for the evolution of the large scale part of the tracer field. And the inevitable problem that we have is that these large scales are going to be forced by this extra term here, this grad dot f, where f here I will call the eddy tracer flux. And this eddy tracer flux is a vector which contains all of the small scale terms, so all terms which aren't the large scale ones. And the problem that we have is that in our coarse resolution ocean models, as opposed to eddy resolving ones, this grad dot f is not available to us. So we do not resolve this term in these most ocean models. Currently, it's very common for oceanographers to approach this problem by parameterizing the eddy tracer flux by invoking something called the flux gradient relation. So that's this equation here. So what this does here is relates the eddy tracer flux F to the large scale tracer gradient by some transport tensor K. So if we're considering isopycnal transport, then this transport tensor in its most general form is a 2x2 matrix. This transport tensor, capital K, it quantifies both advective and diffusive effects of the mesoscale eddies. In place of this transport tensor, you might see a lot of studies and implementations in ocean models which use scalars instead, or a diagonal tensor. So both scalars, diagonal tensors, and the transport tensor, they're all able to account for the inhomogeneity of eddy transport. By that I mean they're all able to have some kind of dependence on space, such that they can quantify the fact that the eddy transport depends on where you are in the ocean. But the scalars and diagonal tensors are much poorer when it comes to modeling the anisotropy of eddy diffusion. So what I mean by anisotropy is the idea that the magnitude of eddy diffusion, which is a part of the eddy transport, I'll go into some more details later, this eddy diffusion has a dependence on direction. So this is the idea that some particles will spread preferentially in some directions over others. So to illustrate the problem, this concept of anisotropy, I've taken this image from Ripina et al., where et al. Might be one or two of the audience members. These ellipses here represent the direction of preferential spreading of some particles that are synthetic particles released into the ocean. So when an ellipse is stretched, that implies that particles are preferentially spreading in that direction. And when it's compressed, it means that particles are less likely to spread in that particular direction. What we find quite commonly from lots of studies is that these ellipses tend to be stretched in the direction of the mean flow or the large scale flow. This is a somewhat well-known property of the anisotropy of eddy diffusion. Then the problem that we have when we use scalars instead of a transport tensor, or diagonal tensors instead of a full transport tensor, is that with scalars, these cannot model anisotropy at all. With diagonal tensors, they impose that the preferential direction of mixing is aligned with the model grid, which is unrealistic. So for the rest of this talk, I'll proceed with this transport tensor representation, which can wholly account for the anisotropy of eddy transport. So the big issues that we have when we trying to parameterize eddy tracer fluxes in terms of a transport tensor, I've summarized some of them on this slide. So the big one, the main one, is the closure problem. So what I've done when I've used the flux gradient relation is simply recast the problem from a need to parameterize the eddy tracer flux into a need to parameterize the transport tensor. So we still want to be able to somehow represent this transport tensor K in terms of large scale flow features. At the moment, in ocean models, current parameterizations to represent this transport tensor are usually a combination of an isotropic ready diffusion scheme and Jensen-McWilliams advection scheme. Another major problem that we have is that this transport tensor is in fact tracer dependent. So if you were to calculate it for one tracer and calculate it for a second tracer, you would find that the transport tensor is different. This obviously increases the dimensionality of the problem, if that means that we would have to use a different transport tensor for different tracers. Another issue is the ill-posedness of the flux gradient relation. So this is the notion that any up-gradient eddy fluxes will lead to negative diffusivities. I've put diffusivities here in inverted commas because I haven't precisely defined what I mean by this yet, but it's likely well known by a lot of the audience that if you were to implement some kind of negative diffusion scheme into an ocean model, then you'll be met with severe numerical instability issues. So this is the idea of ill-posedness. Another issue is the dependence that the transport tensor has on the scale separation, and the more broad issue of how can we be sure that the eddies that we're modeling are truly representative of those that are missing in coarse grid ocean models. And the last issue I've highlighted at the bottom here is the validity of the flux gradient relation. So this is a much more fundamental problem. The flux gradient relation, which is invoked in hundreds of studies, relies on a scale separation between the large scales and the small scales, the large scales and the mesoscale eddies. But it's quite well known that this scale separation doesn't truly exist in the real ocean or in our numerical models. In this case, it may not actually be true that the eddy fluxes are actually proportional to the tracer gradient. So I've highlighted 5 different issues here. With these being said, I'm going to proceed with an approach where I use a transport tensor to quantify eddy tracer fluxes in the ocean. I just think it's very worthwhile to keep these kind of issues in mind. So our approach. So I'm going to first describe the ocean model that we use. So for the rest of the talk, I'm going to be showing results that are obtained using a QG quasi-geostrophic ocean model in a 3-layer double gyre regime. So this, I won't dwell on it for too long, is involves solving a prognostic equation for your potential vorticity anomaly in each of your 3 layers. K here represents the layer index. The potential vorticity in the upper layer is forced by a wind forcing, a double gyre wind forcing pattern. In the bottom layer is forced by bottom friction. This is the nonlinear advection term. And this term here just represents the idea that our ocean basin is set up to be a beta plane. So it's with beta selected with this value here so that it's representative of a northern hemisphere mid-latitude basin, such as the North Atlantic. Another important detail of the model is that it's 3 layers, and these layers are initialized with isopycnal thicknesses of depths of 250 meters, 750 meters, and 3 kilometers. And then lastly, another feature of the QG model is that to solve the potential vorticity equation, you also need to get the stream functions and size at all times. And we solve those by also solving these elliptic equations for the stream functions at every time step. These stream functions are what define the flow in each of our 3 layers. So we've defined our ocean model. What we also have to do then is decide how we're going to separate our large scales and our eddies. How are we going to define what our mesoscalar eddies are given an eddy-resolving simulation? So at this point, it's really common for studies to invoke a Reynolds decomposition, where eddies are typically defined as a deviation from a time mean or a zonal mean. What I'll do instead is separate scales using a spatial filter. So this kind of approach using a spatial filter is much more common in the context of large eddy simulation studies as opposed to oceanographic ones. With a spatial filter, we'll actually lead to a large scales and eddies that have full spatio-temporal dependence, which is in stark contrast to Reynolds decomposition, which imposes that the large scales are constant in either time or space. So there are 2 main options when it comes to using a spatial filter. One of them is a Gaussian shaped spatial filter, but what we'll use is a square spatial filter, so that given a field psi, so the indices here represent the grid indices. Given a field psi, its large scales is defined by taking an average of all grid points, which are spanned by the square spatial filter when that filter is centered on grid point ij. So you can more succinctly express that spatial filter in the form of a double sum, where one sums over zonal grid points, and the other sums over meridional grid points. So zonal east-west and meridional is now south-north. The single parameter of a square spatial filter is its width. And for reference, we take the width of this spatial filter to be 112.5 kilometers. And just to provide a bit of context, that is approximately 3 times the first baroclinic Rossby deformation radius in an ocean which has a side length of 3,840 kilometers, representative of, say, the North Atlantic Ocean, and a grid resolution of 3.75 kilometers. So that means that the filter spans 31 grid points in the horizontal direction. So we use this filter to find our large scales, and then the eddies, which we denote using a prime here, is simply taken as the difference between the large scales and the full flow. So in this figure here, I just illustrate the flow solution, and I illustrate the effects of the scale separation. So on the left is the upper layer potential vorticity anomaly. So this kind of flow regime might be familiar to some of you. I'll just point out some of the main characteristics. This is the PV anomaly in the upper layer. So in the west, we have a very strong western boundary current, which feeds the eastward jet extension. And this jet extension has flows speeds on the order of 1 to 2 meters per second. The jet is being characterized here by a sharp potential vorticity gradient. In the middle, I showed the large scale part of the potential vorticity anomaly. So for all intents and purposes, this is simply a smoothed version of the full potential vorticity anomaly. And then on the right-hand side, I show the eddy part of the potential vorticity anomaly. This includes lots of small scale features like filaments, vortices, lots of sharp gradients, which when added back on to the large scale part will sharpen lots of the features that we see in the large scale part. What we also need to define is our tracer equation. So the tracers in our model are then advected about the domain by the geostrophic velocity, which is given by the stream function outputted by the QG model. Tracers are also subject to subgrid diffusion. So this represents the effects of scales that are too small to be modeled by even our mesoscale eddy-resolving grid. Tracers are also forced by this extra relaxation term, R, which I will describe a little more detail in a couple more slides' time. For the entirety of this talk, I'm going to focus on just 2 tracers. One tracer here, which is initialized with a simple linear zonal gradient, C1 equals X, and a second tracer, which is linearly initialized with a meridional gradient, that's C2 equals Y. Of course, what we're actually interested in is the role that mesoscale eddies play in forcing the large scales in this equation. So we can write down, similar to before, the large scale tracer equation as advected by the large scale velocity. And we find that it's forced, just as before, by the eddy tracer flux or its divergence, where the eddy tracer flux or its divergence in equation 9 is given by this rather general looking form. And it has this general looking form because we use a spatial filter as opposed to a Reynolds decomposition. So you notice that I've defined it in terms of its divergence. I do this because for a general spatial filter, it turns out that the filter operator will not commute with the divergence operator. So you can't take the filter operator inside of these brackets here. For our choice of spatial filter, the square spatial filter, we find that it does commute with the divergence operator at all grid points, apart from a very small number of grid points that are near the lateral boundaries. So away from the boundaries, so at the vast majority of our grid points, we do have an explicit expression for the eddy tracer flux in black here. So this is a much more familiar form of the eddy tracer flux for large eddy simulation studies and much less familiar for oceanographic studies. It's quite common to then see an eddy tracer flux of this form separated into 3 parts: a Leonard flux, which is this one in red, a pair of cross fluxes, which are these ones in blue, which are the interactions between the eddy terms, the prime terms, and the large scale terms. And then on the right in pink, a familiar Reynolds type flux. You might notice as well at this point that if we were to change our minds and redefine our large scales and eddies to be a time mean and a deviation from the time mean, then this Leonard flux would go to 0 and the cross fluxes would go to 0. And then you'd just be left with the Reynolds type flux. In our case, though, with the spatial filter, we find that all three of these terms are equally important, and more importantly, that they have significant cancellations with one another. So this means that it makes most sense to consider the sum of them at the same time rather than considering them separately, because cancellations between each of these three terms represent balances that exist in the eddy budget, and we're not interested in the eddy budget. We're interested in the role that this flux plays in the large scale budget. Another property of this eddy tracer flux F is that it has a non-divergent part, which is inert. It doesn't affect the evolution of the tracer field, but dominates the divergent part by 2 orders of magnitude. So we want to remove this part because it has a obscuring effect on any kind of interpretation of the eddy tracer flux. And we remove it by, first of all, setting this potential psi, by setting its Laplacian to be equal to the divergence of the eddy tracer flux. We can invert this equation with boundary conditions that say that this divergent eddy tracer flux is 0 on the boundaries. Once we get the potential, we can take its gradient, and then that is equal to the divergent part of the eddy tracer flux. So from here on, I'm going to work with the divergent part only of the eddy tracer flux, and I've removed its non-divergent part. If you recall, on the right-hand side of the tracer equation, there was this extra term, a relaxation. Specifically, it's a relaxation of the large scale part of a tracer field back towards its initial condition. For this, I use a relaxation rate, which has a time scale corresponding to 5 days. I've looked at, over the course of doing this research, a whole range of different relaxation timescales, and all of the conclusions that I'm going to talk about today are independent of this choice of the relaxation rate. So there are a couple of different ways that we can motivate including a relaxation like this in our tracer equation, one of which I won't be able to provide the proper context for just yet, and that we'll have to wait a few more slides. But another important motivation for including a relaxation is that real world passive tracers in the ocean do undergo sources and sinks which can have effects akin to a relaxation. So for example, for temperature, they undergo air-sea heat fluxes. For oxygen and carbon, they are also exchanged between the air and the sea. Salinity undergoes large-scale sources and sinks because of the processes of precipitation and evaporation. And for some minerals like nitrate, they are also undergo sources and sinks due to processes like remineralization and fixation. So these are just a couple of snapshots of the tracer field from our simulation as advected by the geostrophic velocity. So on the left, I show the large scale part of our tracer field minus its initial condition. This is for the first tracer, tracer C1, the one which is initialized with the zonal gradient. On the right, I show the eddy part of the same tracer, so adding these back together, and if you were to add on its initial condition, you'll get the full tracer field. I'm not going to dwell too much on these specific snapshots because these are almost entirely tracer dependent. So if you use a different initial condition, you'll get a completely different looking result. I'd just like to point out that large scale features do certainly develop in the tracer field, and these are significantly forced by the eddy tracer flux. The eddy field of the tracer contains, much like the PV anomaly, lots of sharp gradients, lots of filaments, lots of vortices, and lots of complicated swirling patterns. You might notice that along the jet here, we have a very consistent region of low tracer concentration. So low tracer concentration is represented by the darkest blues. And this is simply because the jet is advecting weak concentrations of tracer, which are in the west, towards the east. So in effect, the tracer concentration is reduced across all latitudes, longitudes by the eastward advection by the jet. So, and now what we're really interested in is the role that mesoscale eddies play in forcing that large scale tracer evolution. So I'll come back to the flux gradient relation. This is just the same as it was written down before, but instead of the eddy tracer flux, I've got its divergent part. But what I'm going to do going forwards is just continue to refer to this as the eddy tracer flux just for brevity. You might have noticed that this flux gradient relation is a system of two equations, but the transport tensor has four unknowns. This means that this system is actually underdetermined. So we cannot readily get a solution, the transport tensor solution. To solve this problem, I introduce a second tracer C2. So this is the one which is initialized in our case with the linear meridional gradient. We can compute its divergent flux, just like we can compute the divergent flux for the first tracer. And once we have these two tracers, we can invert equation 15 to get an explicit expression for this transport tensor. And we find that it is the product of two matrices. The first matrix is just made up of the components of the two eddy tracer fluxes. The second matrix is made up of the large scale tracer gradients. And then the product is divided by this determinant here, where the determinant is essentially the product of the different tracer gradients. So it's the determinant of this matrix of tracer gradients here. You'll notice that if these tracer gradients, C1x, C1y, C2x, C2y, if the tracer gradients align, then this determinant becomes 0, and this k would then explode to infinity. So this is our second motivation for including the relaxation of the large-scale tracer fields, because we need to maintain misalignment of the tracer gradients throughout the simulation. Without it, d would be 0 and k would blow up to infinity. So now I'll just give some more useful properties of this transport tensor. I mentioned very briefly earlier that the transport tensor is non-unique, meaning that it depends on the tracers which it's computed. But the non-uniqueness isn't quite as pathological as it might first seem. So if you have tracers C1 and C2, then we can exploit the linearity of the flux gradient relation and the linearity of the tracer equation. And doing that, we can show that the transport tensor K is the same for any tracer pairs that are linear combinations of the first two tracers. So what this means by extension is that the transport tensor is the same for all tracers which are initialized with linear initial conditions. So we've chosen tracers with initial conditions X and Y. We could have amplified or rotated those gradients as we please, and we'd actually find the same transport tensor as a result. So the transport tensor that we obtain is more general than just applying to the two tracers that we're showing results for. It's extremely useful to separate the transport tensor into its symmetric and anti-symmetric parts because they represent different effects. The symmetric part, S, I'll refer to as the diffusion tensor, and this quantifies diffusive eddy effects. Its anti-symmetric part, which is A, I will call the advection tensor, and that quantifies advective effects. So for the remainder of the talk, I'm going to talk about the diffusion tensor and the advection tensor, which sum to give the transport tensor. I'm going to talk about these separately because this aids a physical interpretation of their effects. So I'll start with a few slides on the diffusion tensor. So the diffusion tensor has three unique entries. It has its off-diagonal entries, and then its diagonal entries, and then its two off-diagonal entries are equal to one another. So just three unique entries. But it's most useful to characterize the diffusion tensor instead in terms of a diffusion angle and a pair of eigenvalues, the diffusion eigenvalues. So the diffusion angle represents the angle of the principal axis of the diffusion tensor, and you can compute this diffusion angle using this inverse tan of the elements, which would be consent inverse tan of the this fraction with the elements of the diffusion tensor. Once you've got the diffusion angle, you can then calculate the two diffusion eigenvalues using a combination of the entries of the diffusion tensor and these cosine of alpha and sines of alpha. It's useful to compute the eigenvalues in this specific way because doing this guarantees that the first eigenvalue is greater than the second eigenvalue. So these diffusion eigenvalues are what represent the diffusivities of our eddy diffusion. The alpha is a diffusion angle, so this quantifies the direction of preferential down gradient diffusion. So it's in essence a quantification of the direction of this anisotropic eddy diffusion. So lambda 1, the first diffusion eigenvalue, corresponds to an eddy diffusivity in the direction of the diffusion axis, which is the first eigenvalue of the diffusion tensor. Is the principal axis of the diffusion tensor and has this simple form cos alpha sine alpha. Lambda 2 is the second diffusivity that corresponds to a diffusivity in the direction which is perpendicular to the first one. Then just for concreteness, the diffusive flux, which is one part of the full eddy tracer flux, is simply calculated by taking the product of the diffusion tensor with the large scale tracer gradient with a minus sign in front. And then just for a bit more useful information, this diffusive flux in ocean models is typically parameterized using isotropic ready diffusion. So here are some snapshots of the eigenvalues. So the first eigenvalue on the left, the second eigenvalue in the middle, and the diffusion angle on the right. So the first important property of these two eigenvalues that I want to draw your attention to is the fact that the first eigenvalue is positive almost everywhere in the ocean. The second eigenvalue is negative almost everywhere in the ocean. So this is a snapshot in the upper layer. So I'll refer to these opposite signed eigenvalues as polar eigenvalues. So this means that the first eigenvalue represents a tendency to induce a down gradient eddy diffusion flux in the direction of the diffusion axis. That this eigenvalue is negative represents that it has a tendency to induce an up gradient flux in the direction perpendicular to this one. So this means that the corresponding eddy diffusion is completely anisotropic, much more anisotropic than has been previously diagnosed in previous studies. One of the reasons why the anisotropy is more, or has a potential to be more pronounced than is diagnosed in previous studies, is because lots of diagnostic methods are biased against diagnosing any kind of negative eigenvalues. The diffusion angle on the right quantifies the orientation of the preferential down gradient eddy diffusion. So this is an angle which runs from pi by 2 to minus pi by 2. It's only pi periodic. So the darkest reds and the darkest blues are equivalent to one another. I'll highlight some important properties of this. One property is that it has a tendency to lean into the shear of the eastward jet in this region. Another property for more general areas of the ocean is that the diffusion axis has a tendency to be aligned with the large scale velocity vector. So this actually is in quite close agreement with the findings of lots of past studies, which have found that the down gradient diffusion quantified by this eigenvalue has a tendency to preferentially occur in the direction of the large scale flow. And that's what we find also. A more general point that I'd like to make about all of these fields is that they exhibit very significant spatio-temporal variability. The main reason for this relative to results from past studies is that we use a spatial filter scale separation, which includes much less averaging than the more common diagnostic techniques. So I'm just going to go into a little bit more detail on these polar eigenvalues. So In this figure here, I show a couple of PDFs of the distributions of the eigenvalues. So on the x-axis represents the values for the first eigenvalue. The y-axis represents values for the second eigenvalue. This panel on the right then is the distribution of the eigenvalues from our reference simulation, this time in the deep ocean as opposed to in the upper ocean. So the darkest reds and oranges represent where there is a high frequency of eigenvalue pairs. So you'll notice that there aren't any, the top left corners of these panels are all entirely white because the first eigenvalue is greater than or equal to the second one. But the greatest concentrations are in the bottom right-hand corner. This essentially is just confirming that eigenvalues of opposite sign are most common. The panel on the left is the same as this one on the right, but we've just weakened the relaxation. So in this case, the relaxation has a time scale of 100 days as opposed to 5 days. The eigenvalues in this case are a little bit stronger in amplitude. I'm not going to talk today about the reasons for that, but I just want to use this to illustrate that the polarity of these eigenvalues isn't very strongly affected by the choice of our relaxation. It's also the case that polar eigenvalues are a prevalent feature when we use a general circulation model, which simulates the primitive equations in place of the quasi-geostrophic model. We've also observed these polar eigenvalues to be a very common feature for a range of spatial filter sizes and for eddies defined to be the deviation from the time mean. So the result of polar eigenvalues in our diffusion tensor, so these opposite sign diffusivities, is a very robust one. So what do these actually represent? What do the fluxes do? So with polar eigenvalues, the diffusive flux will generally filament the tracer field. So what we'll see the diffusive flux doing is typically stretching a tracer patch in one direction, in the direction corresponding to the first eigenvalue, and compressing it in the transverse direction, the direction corresponding to the second eigenvalue. This doesn't tell us anything about whether or not the full flux, this net effect of these two diffusion eigenvalues, it doesn't tell us whether or not the full flux is actually up gradient or down gradient. So this leads us on to the question of whether or not this diffusive flux is actually diffusive. Up until this point, I've been using the word diffusive to refer to a process which transfers variance between the large scales and the small scales, whereas more classically, diffusive is used to specifically refer to processes which transfer variance down gradient from the large scales to the small scales. So to check whether or not our diffusive flux is actually diffusive, we can look at this variance transfer. And the variance transfer we can compute by simply taking the dot product of the eddy tracer flux with the large scale tracer gradient. There's a minus sign in front of it, so that positive values of this correspond to down gradient transfer, diffusive transfer. This is the same as just taking the dot product with the diffusive flux in place of the full eddy flux. This is essentially the definition of a diffusive flux. And we can actually show that this expression is equal to this handy expression in terms of the diffusion eigenvalues, λ1, λ2, the diffusion axis, the magnitude of the tracer gradient squared, and omega here is the orientation of the tracer gradient. It's the orientation of this grad C over bar. So you'll notice that this variance transfer is contributed to by two terms, one corresponding to λ1, one corresponding to λ2. And the signs of the transfer is entirely determined by the signs of the diffusion eigenvalues, or the signs of their contributions, I should say. So this confirms that if we have opposite signed eigenvalues, then the diffusive flux is the sum of a down gradient flux and an up gradient flux. But because of this dependence on the difference between the diffusion angle and the orientation of the tracer gradient, we still can't conclude whether or not the total flux is up gradient or down gradient. So what we can do instead is just actually plot this variance transfer directly. So I'm showing you another PDF, another two-dimensional histogram with darker colors representing, the darker reds representing high probabilities of variance transfer values. So on the x-axis of this PDF is the variance transfer for the first tracer. On the y-axis is the variance transfer for the second tracer. So this is aggregated over all grid points in our upper layer of the ocean for 1 year's worth of data. What you'll notice here is that instances of up-gradient variance transfer by the diffusive flux are extremely common. So that's anywhere where the variance transfer values are negative. So these up-gradient transfer regions are extremely common, which is, in some sense, it might be seen as a very surprising result because for the moment, parameterizations of eddy diffusion in the ocean exclusively parameterize down-gradient transfer, whereas we've diagnosed up-gradient transfer to be pretty much just as common as down-gradient transfer. A very useful finding that we also have, though, is that if we take a snapshot of the variance transfer and look at its domain mean, we find that at all times, the domain mean diffusive flux is down gradient. So at all times, we find that the diffusive flux is on average down gradient. But, and this is the important result that we have here, is that these instances of up gradient transfer are very common. And these up gradient transfer instances are absolutely not parameterized by any kind of closure implemented in ocean models at the moment. So I've finished talking for now about the diffusion tensor, and I'm going to spend a few slides now talking about the advection tensor. So that's the part of the antisymmetric part of the transport tensor, which parameterizes advective effects. So these advective effects can be represented in one of two ways and exploit the fact that the advection tensor is an antisymmetric tensor with a single unique entry with a minus sign in the top right and without a minus sign in the bottom left. So the most direct way to represent these advective effects is by simply taking the product of the advection tensor with the large scale tracer gradient with a minus sign again to get the skew flux. And it's called a skew flux because it's perpendicular to the large scale tracer gradient. But the same eddy effects can be represented by the advective flux. This is the one that we're going to focus on a little bit more. And to define the advective flux, you need to additionally define an eddy-induced velocity, or an EIV. In our case, this eddy-induced velocity is just a rotational velocity, which has a stream function A. So its stream function is simply the entry of the advection tensor. So the defining factor of this skew flux and the advective flux is that they do nothing to dissipate variance. So they play no role in the transfer of variance from the large scales to the small scales. Just as a reminder, so the Jensen-Williams famous parameterization from 1990 is used to parameterize this eddy-induced velocity and the advective flux. This is what is implemented in most ocean models, or probably all ocean models. Griffiths came along in 1998 and showed that the Jensen-Williams eddy-induced velocity can be recast in terms of this skew flux form. So both the skew flux and the advective flux form of the Jensen-Williams parameterization are implemented in the majority of ocean models. So here on the left, I show the upper ocean time mean stream function, A. That's just the off-diagonal entry of the advection tensor. So the time mean is evaluated over just 1 year of data. So I think it is easiest to reach some kind of interpretation of this by considering it as a stream function rather than as a component of the skew flux. And in this case, you might recognize that the corresponding eddy-induced velocity actually contains 4 rotating, large-scale rotating patterns, which circulate around the low stream function, high stream function regions. to get a more statistical description of the properties of the corresponding eddy-induced velocity, you can compare it with some features of the large-scale flow. That's what I do with this histogram on the right-hand side. So what specifically I'm looking at here on the right is the angle between the eddy-induced velocity, U star C, and different features of the large-scale flow. So in orange and green, these ones that peak in the center, near angles of pi/2, I'm plotting the angle between the eddy-induced velocity and the large-scale relative vorticity gradient in orange, and the large-scale thickness gradient. So that's the isopycnal thickness gradient, the gradient between where thickness is the difference between different density surfaces. But I want to draw attention instead to the blue one, which is the one which peaked near values of pi, because this is the angle between the eddy-induced velocity and the large-scale velocity vector. What this tells us is that typically this eddy-induced velocity is oriented in the direction opposite to the large-scale flow. What's also important is that this eddy-induced velocity has magnitudes very similar to the large-scale flow. So in the jet region, around here, it has speeds on the order of 1 meters per second. Elsewhere, it has speeds on the order of 1 centimeter per second. So the sum of the large-scale velocity vector and the eddy-induced velocity vector is quite aptly referred to as a residual velocity, because the two velocities will have significant cancellations with one another. And this notion of the large-scale velocity and the eddy-induced velocity opposing one another, and therefore being referred to as a residual, is not new at all. Some of the earliest diagnoses of eddy-induced velocities in the ocean have found this property to exist. So this provides essentially another link with our findings and those of lots of past studies from recent decades. When we're talking about the concept of eddy-induced advection for passive tracers, it's very useful to consider it in the context of eddy-induced advection eddy-induced advection of mass. And the reason for that is because in ocean models, the eddy-induced velocity, which is actually parameterized for both passive tracers and mass, is determined from a mass analysis. So again, I'm referring here to the Jensen-McWilliams GM parameterization. So just to illustrate this a bit more clearly, there's two ways in which we can write the large-scale tracer equation. So in equation 30, this top one here, this is the approach that we've taken in this study. So ignoring the external forces, the subgrid diffusion and the relaxation, this is what our large-scale tracer equation looks like. So what I've done here is simply recast the eddy tracer flux in terms of the diffusion tensor and its representation in terms of also the eddy-induced velocity. What Jensen-McWilliams did in 1990 was take an approach where they combined the tracer equation with the equation for isopycnal thickness or mass. And when you do that, you can show that the large-scale tracer field is actually also advected by this term in red here, where FH, the top term, is the eddy mass flux, or eddy thickness flux if you're working in an isopycnal model. And H bar is the large-scale isopycnal thickness. So Jensen-McWilliams in their 1990 paper and the follow-up 1905 paper defined this fraction to be the eddy-induced velocity for mass or thickness, isopycnal thickness. And when you write your equations down like this, you get this other right-hand side, which is a function of eddy terms of velocity, tracer, and mass. I've noted these two right-hand sides as right-hand side 1 and right-hand side 2. So what Jensen-McWilliams did in their parameterization was parameterize this eddy-induced velocity and then assume that this entire right-hand side represents eddy diffusion. So now you can see, given that there are these two different ways to represent our large-scale tracer field as being advected by different eddy-induced velocities, a natural question is then to ask is whether or not these two velocities are the same, or in other words, are these two right-hand sides the same? If they're not, it might throw into a small bit of doubt as to whether or not the Gentleman-Williams eddy-induced velocity indeed parameterizes all advective effects on passive tracers. So here I'm showing another histogram. This time it's a histogram of the angle between the eddy-induced velocity computed from my tracer analysis and the eddy-induced velocity calculated from the mass analysis. So histograms of this, the angle, sorry, between this vector and this vector. What we see here is that essentially these two vectors are very, very weakly related. The correspondence between U star C and U star H is very weak. What this tells us then is that not all eddy tracer advection is accounted for by this mass determined eddy-induced velocity. What it tells us more generally is that care has to be taken when parameterizing eddy-induced advection and eddy-induced diffusion. You have to make sure that your diffusion scheme and your advection scheme are consistent with one another. If, for example, you are implementing the Gentleman-Williams parameterization based on parameterizing this eddy-induced velocity, then you don't want to then parameterize this diffusion tensor, because evidently this diffusion tensor or these diffusive effects on the right-hand side are not likely to be the same as these diffusive effects here. And this represents a more general issue, which is there's a certain ambiguity with regards to the classification of diffusive and advective eddy effects. So in my penultimate slide, I'll just ask the question as to whether or not we can parameterize the transport tensor that we've diagnosed. So there's some initial preliminary findings suggest that it may be possible to do this. For example, we find that there is a very weak negative correlation exists between the transport tensor and the velocity gradient tensor, which implies a closure of this form here for the divergent part of the eddy tracer flux. It's proportional to the product of the velocity gradient tensor and the tracer gradient. So this is actually very similar to a model which has been proposed in a handful of large eddy simulation studies. The model is called the gradient model, and it's been proposed for not just passive tracers, but active tracers like PV and relative vorticity. What is particularly interesting about this kind of closure, we're using the velocity gradient tensor to represent the transport tensor, is that the corresponding diffusion tensor, so the symmetric part of this, is the strain rate tensor. And this strain rate tensor for non-divergent or weakly divergent flows has opposite signed eigenvalues, just as was found for our diffusion tensor. I strongly suspect that much stronger relationships exist between different large-scale flow features, but we've yet to find these. But hope does lie in the potential use of some machine learning models. For example, Lausanne and her research group have looked at uncovering relationships between eddy fluxes and large-scale flow features using different machine learning models, such as relevant vector machines. The issue, of course, with using these kind of machine learning models is that it's very difficult to get the supporting theory for any models that your machine learning model might diagnose. And just at the bottom here in this slide, I'd like to just remind of the notion that the flux gradient relation itself may actually be an incomplete model of eddy transport, by which I mean that it may be necessary to introduce higher order derivatives of C on the right-hand side of this equation. And this again relates to the idea that this only including linear first order gradients in the of the large scale tracer field is a consequence of us assuming that there is a scale separation between the large scales and the eddies, which doesn't truly exist. So in my mind, I think it would be a very worthwhile approach to start looking at alternatives to the flux gradient relation, which look for possibly higher order, which look at using higher order derivatives of the tracer field. So I'll just summarize what I've been talking about these last few moments. So what we've done is look at a brute force approach to diagnosing the full transport tensor for isopycnal eddy tracer transport. One of the key steps that we've taken is separating the large scales from the eddies using a spatial filter as opposed to using a Reynolds eddy decomposition. This kind of spatial filter approach is arguably more suited to eddy permitting ocean models as opposed to non-eddy resolving. But I would argue that it's also applicable to the non-eddy resolving models as well. The resulting transport tensor that we get from the flux gradient relation is non-unique. So it depends on the traces for which we calculate it. And given this and the fact that we observe a relatively weak relationship between the transport tensor and features of the large scale flow suggests that a stochastic parameterization for K might be more suitable. We've separated this transport tensor into diffusion and advection tensors to separate the diffusive and advective effects. So the main feature of the diffusive part is that the diffusion tensor is characterized by these opposite signs, so polar eigenvalues, implying that the corresponding diffusive flux is responsible for the filamentation of tracer fields. We've also found that the eddy advection is just as important as the eddy diffusion, but it may not be diagnosable from mass analysis. If anyone would like any more details on any of the results that I've spoken about today, then our results are spread across a handful of papers. So it's a couple in ocean modeling, one in JFM, one in geophysical research letters, and one in the deep sea research as well. Thank you everyone for listening. Thanks a lot.
Thank you, Mike, for an excellent seminar.
Thank you.
Time for questions.
I have a little questions. Did you do all your experiments with a filter width of 31 grid points?
No. So in this DSR1 paper, we've looked at, which shows, I think, 3 or 4 different filter sizes. We also looked at eddies, which are defined using the more classical time mean and deviation approach, and found that, well, all of the conclusions which I highlighted today were insensitive to the choices of either the spatial filter size or the use of a spatial filter over a Reynolds decomposition.
So did you try filter widths that are 100 grid points or 1,000 grid points to see if the results do change? I would have expected that the results would be sensitive to multiplying by 10, maybe not multiplying by 4 or 5.
So
that implies a huge grid.
So no doubt that like the spatial patterns of the transport tensor entries look different, but the prevalence of these opposite signed eigenvalues, or the relationship that the transport tensor has with the large scale flow, or the role that eddy advection plays, are largely the same. So these statistics are the same, but yes, the spatial patterns of the fields that we diagnose probably won't be the same. I think that Llewellyn-Sun, who's also been working on this problem, might have looked at some obscenely large spatial filters as well. But off the top of my head, I can't remember what conclusions she might have made from that.
Because wouldn't that tell you a little bit about the scale separation issue? Averaging over 10 versus like 1,000 points?
Yeah, Yeah, it could. Yeah, I think it would. It might be able to tell us something about the scale separation issue. But yeah, I'm not. I don't think I'm able to speak anymore on it. I'm not. Can't recall any of the findings of Llewellyn when she looked at these very, very large spatial filters.
Okay.
A quick comment, of course, you want to preserve a meaningful large-scale field. And in this case, your Gulf Stream, for example, would be severely distorted by a very large filter.
Mm-hmm.
I was thinking more like increasing the resolution of the fine model as opposed to the one of the coarse model.
So yeah, I would suspect that, certain features such as the polarity of eigenvalues, I suspect that that is here to stay. I think there's theories that sub-mesoscale eddies do quite a lot in driving tracer filamentation as well. And they're also likely to be represented by polar eigenvalues if they were to be parameterized using a diffusion tensor.
Mike, I have a question. So as you develop, as we try to develop eddy parameterization schemes, how do we decide if the scheme is working? What kind of criteria would you use to make that decision?
I think first and foremost, I think I'd be tempted to use simple visual checks. We want to maybe identify certain large scale features and see if we're able to reproduce them in some kind of parameterized model. There are obviously, what we found is that there's huge difficulties when you start to use point-wise comparisons between raw fields and then some parameterized simulation. We find that you might have a reproduced field and an original field that look very similar by eye, but have huge differences when you subtract them grid point by grid point. So I think that kind of point-wise differencing is not a very useful approach because that leads to very pessimistic estimates of errors. So yeah, I would first and foremost suggest using just visual checks. And then what we have to define is some kind of large scale spatial comparisons, which takes multiple grid points into account as opposed to just single grid points.
Thank you. I think Pavel raised his hand first, and then Arthur, and then Yo-Yang. Pavel, can you go ahead?
You might be muted.
I don't think. Oh yes, he's muted. Pavel, you're muted. Okay, maybe you should let Arthur ask the question while Pavel is resolving.
Okay,
Yeah.
I'll first of all, that was an awesome seminar. Thank you for taking the time to give us some fresh ideas to think about. I'm a big believer in stochastic dissipation operators. The present approach is not the right approach. I like your analysis that showed the negative diffusivity. I did analysis of drifters in the ocean where I showed the same thing, that the negative diffusivity does happen a lot, but on the average, we get the right sign. But there are still many instances where you're seeing the flux the other way. Just a couple comments. You picked the boxcar filter. It's computationally convenient, but I don't think you could pick a filter that has worse filtering characteristics than a box filter. I'm just curious about that choice.
Mm-hmm. So one thing I'd like to point out is that I don't think that these results will be that sensitive to changing to a Gaussian filter. So there are studies that have recently used Gaussian filter to look at similar problems and find similar results. If I were to repeat this process, I probably would upgrade the filter. Our motivation at the very beginning was, like you said, using the very simplest filter that we could think of. And then extending to more complicated filters. It just so happened that we somewhat fell down the rabbit hole when we started to examine results using this simple filter. The results started to take hold of us a little bit, and it felt like we had to first understand results for this most basic filter before moving on to something more, moving on to different ones.
Oh, quite understandable, and I totally agree with that philosophy of just pointing out that it's probably maybe another better filter to use. Now, I'm curious about your choice of tracers to use. You say you run into a ill-posedness problem, so you need to pick 2 tracers to get past this ill-posedness problem. How do you know the tracer concentrations are not so highly correlated that picking 2 is the same as picking 1? So in your case, what 2 traces were you looking at?
So a tracer initialized with a linear zonal gradient, and then a second initialized with the linear meridional gradient. So over the course of this whole work, we've also looked at a few with nonlinear gradients. Yeah. So like I said, most of the conclusions that I discuss in this talk, the ones basically given the broader statistics, are the same for different tracer initializations. The specific spatial patterns of, say, the transport tensor are different. Maybe not very drastically so, but they are a little bit different. And the other benefit of using these linear tracer pairs is that it's actually, then you actually get the same transport tensor for every single pair of linearly initialized tracers because of the linearity of the flux gradient relation and the tracer equation.
Thank you, and thank you again for such an amazing seminar. Appreciate it.
Thank you.
Can we try Pavel now? Pavel? Still, we cannot hear him. Yu Yang, I remember you raising your hand.
Yes. Hello, Mike. That's a nice talk. So I wonder, you have shown that the Full-Tensor has many properties, the properties of eddy-induced transport. So what property of the Full-Tensor do you think will have the largest effect on the largest scale tracer? Or what part?
Sorry.
Or what part of the Full-Tensor do you suggest to use in the coarse resolution model? Because it would be extremely hard to use the Full-Tensor in a coarse resolution model, right? So we
of
have
course,
to
yeah, it'd be impossible. Well, I would be very curious to see what a simple gradient model, something like this, how might this perform in an ocean model. It's naturally extremely difficult to pick out certain spatial features of the transport tensor, which I think need to be parameterized. I would say that as a bit of a cop-out answer, that both the diffusion tensor and the advection tensor are just as important as one another. But what I would suggest, I think, would be very interesting to see would be parameterization of this form. This has been implemented in a handful of large eddy simulation studies, but obviously one of the big challenges is overcoming the fact that its symmetric part has a negative eigenvalue. So we're probably actually quite far away from being able to implement this in a stable ocean simulation.
Well,
I hope that represents some kind of an acceptable answer.
Well, you couldn't, speaking as a former developer, right? If your gradients are sharpening, there will come a point where your grids cannot resolve them, and the code will crash. And so, and most codes actually include some sort of limiters to prevent the gradients from growing uncontrollably.
Yeah.
So you might have your parameterization sharpening the gradient and another parameterization decreasing them. So they're kind of fighting each other.
Yeah. So yeah, in the papers that I've read trying to implement a model like this, they also include biharmonic diffusion, which dampens out the really strong gradients. Another thing that we found, of which we have a paper in submission, is very simple case of the diffusion, eddy diffusion, where we have one eigenvalue that's positive and another that's negative, and the instability issues are severely reduced if we allow the diffusion axis to simply rotate in time. If we allow the negative diffusion to persist in a specific direction, then the simulation will blow up after, in the context of an ocean simulation, 100 days. If we allow the direction in which this negative diffusion acts to rotate in time, then what we found is that we can avoid these stability issues, these instability issues for simulations that last something like 100,000 days. So having the direction of these upgradient fluxes vary is possibly key to a stable simulation. Of course, as well, might need to obviously include things like biharmonic diffusion as well. But you're right that it's almost like it kills the strong gradients that the parameterization is designed to create.
Okay, thank you. Sorry, I have another question.
Okay, Young, if you can hold on 1 second.
Okay,
I
sure.
finally got questions from Pavel. I will just read them.
Okay, sure.
Okay, equation 32. Would it make sense to consider both gradients on the right-hand side shifted or delayed in space-time? And the second question, can you recommend upgrading all GCM diffusivities to the polar ones?
So on the first question, I think it would be very interesting to check, yes, if there is stronger correlations between the transport tensor and the velocity gradient tensor if we were to lag the transport tensor behind the velocity gradient tensor, with the implication that this causes the transport tensor. I have a suspicion that that might slightly improve these correlations, but I've not checked. And on the second question, I don't think I understood. Can you repeat it, please?
Can you recommend upgrading all GCM diffusivities to the polar ones? I assume polar. I assume the polarity in the tensor is meant.
Can I? I still don't. I'm sorry. I still don't understand the question there. Can I recommend upgrading
all GCM diffusivities? You know, diffusivities that are used in GCMs. Would you recommend changing it to upgrade
I see.
to the polar one?
Well, that's a very difficult question to answer whether or not I would recommend. At this stage, certainly not, because none of the models would continue to work.
They may not follow your recommendation, but would you recommend?
Well, I think it's certainly something that we should consider taking into account, considering the fact of how prevalent these opposite signed eigenvalues are. It's clearly a systematic effect that mesoscale eddies have on tracer distributions, so we should start working towards incorporating it somehow. I'm of a suspicion, though, that it may be best to not parameterize it using upgradient fluxes because of the inherent stability issues. It may be best to find other ways to do this, perhaps by parameterizing the divergence of the eddy tracer flux instead, rather than the flux itself. So I would be, yes, reluctant to suggest actually implementing these negative diffusivities in all our GCMs. And I think we might have to find a better way of doing it.
Maybe last quick question. Young, you had a question.
Right, yeah. So if I remember it correctly, in one slide, you showed that the net variance transfer is a downgrade. It's downgrading, right? Although there are some upgrading transfer at some instant. So can we use a set of positive diffusivity that has the correct net downgrading transfer?
No,
Without,
the short answer. So to have down gradient transfer, you have to have at least one positive eigenvalue. To have up gradient transfer, you have to have at least one negative eigenvalue. So if both eigenvalues are positive, then it's impossible to have any down gradient transfer.
Okay. Oh, I see. Yeah.
Yeah. So this is also could also be used as another explanation for the prevalence of opposite signed eigenvalues. If at a given instant on grid point, one of the tracers has an up gradient diffusive flux and the other tracer has a down gradient diffusive flux, then it must be the case that the eigenvalues are opposite in sign. But of course, we find that even when both transfers are up gradient, or both transfers are down gradient, we still get opposite signed eigenvalues in both of these cases as well. But yeah, to answer your question, yes, this up gradient transfer can only be represented using a negative diffusivity.
Okay. All right. So, but their net effect, you found that the net effect is downgrading, right?
Yeah. So when I say nets here, I mean the domain mean. So the domain mean of the domain mean of this T, all instances for all the traces that I've looked at, it's always been positive. So it's always been a domain mean down gradient flux, which is at least slightly reassuring that it's not. We don't have these domain mean up gradient fluxes, because that would be even more difficult to parameterize.
Okay, so it is not possible that you just use one positive number to mimic this net downgradient transfer.
Well, I guess it depends how you mean, like as uses one value globally.
Maybe some has some spatial dependence, but they are all positive and so can be implemented in the model.
Well, yeah, that's good. Like that is interesting. So if we can dictate that the variance transfer somehow be positive, be down gradient on average, but permit up gradient transfer in some regions, that might be possible. Then we just have to make sure that we don't have this accumulation of tracer gradients in the regions where we permit the up gradient transfer, and that'll become the challenge. I should point out as well that these, for a given tracer initial condition, which is equivalent to its relaxation profile, the regions where these up gradient fluxes occur are quite persistent. So it's for a given tracer, the up gradient fluxes occur typically in the same regions. In other words, the regions where the up gradient fluxes occur are tracer dependent. So it's not just that it's occurring at random locations about the domain, it's persistent up gradient fluxes in certain locations, which transport by other terms in the tracer equation prevents from leading to singularities.
Okay, thank you.
Okay,
Thanks.
Thank you, Mike. I suggest we thank Dr. Haigh again for excellent seminar, and Dr. Haigh can be accessed. You can continue asking questions by email, and we can continue this discussion offline. Mike, thank you very much. That was a great talk. I certainly enjoyed it.
Thank you, everyone. Thank you.
Bye-bye.
Bye. Take care.